I have a bit of an overview here. Again, to me, it's about understanding and practicing with LLMs, right? I want to give people a better theoretical understanding of what LLMs are doing, demystify them, take away the magic, make you understand, at least to some extent, what they're really doing under the hood. There's a notebook, and I'm happy to share this notebook if anyone requests it. Uh, yeah, very happy to share it. I want to I'll assume people have some background in machine learning, but even if you don't, I think this will still be very useful and helpful. I want to give some exposure to LLMs, generative AI, and understand the core concepts behind them, like the transformer architecture, and hopefully an interactive and intuitive way we can run code, see the code that gets output, and then go from there. I also want to build on the building blocks that kind of got us to GPT-3, GPT-4, 4.0, and this explosion that we're having. But it really starts from like simple building blocks like tokenization, right? Embeddings, attention mechanism, the transformer architecture. And we're going to experiment with all these things. Because at the end of the day, although it's a little, it seems mystical, an LLM is just billions of parameters represented as numbers, and you have numbers as input in. These numbers represent words that somehow represent meaning of words. We'll get into that. We do really just some complex or we actually do some very simple multiplication and addition to these numbers through our LLM. And then on the output, we get numbers that then we map back to words. And the interesting thing is, all an LLM does, ChatGPT, all of them, they predict one word. The truth word is the token, but they predict one word at a time, given all the other words that came before it in the sequence. So you condition it on, hey, here's the last N words that were said. What word should come next? It predicts that. We append it to the sequence, and then we feed that whole sequence again to the LLM and say, okay, what word comes next? And then if that's the whole generation, we use tools like ChatGPT. So that's the kind of the theoretical background. I'll walk into it through these things in the notebook. And again, this is a huge compression of like what would normally be like a 12-week course, a lot more details. But first, I want to give you something to walk away with. I like to show the end first, and I like to show the practical things first. So there are fantastic resources out there to develop LLMs, and you yourself can develop one, right? Various machine learning engineers like myself, you could use PyTorch, you could use Hugging Face. For this workshop, we're going to use a relatively new but really growing popular library from Unsloth. That's what they're called, to fine-tune LLMs in a really compute and memory efficient way. It's a typo. They have several tutorial notebooks. I can actually go to their website and show you them. Again, I've just found them myself. They're great, and the community is having great success with them. You can go and actually do common operations on common LLMs. Familiar with the latest frontier models and open weight models, Llama 3.1, 3.2, Google's Gemma, Alibaba's Qwen, Microsoft's Phi, all these open weight models, and we can do other operations on them. I can click them, and the great thing is one of the greatest restrictions, unfortunately, with LLMs is they require a lot of compute. Unsloth is very, very generous, and they actually will let you use, through their Colab notebooks, a relatively, fair-sized GPU. They're allowing me to use a T4, which has, 13 gigs of RAM and has the benefits of GPUs. Let's say, you guys want to fine-tune your own LLM. I'm going to walk you through that now, and then we're going to work backwards and understand the theoretical concepts behind all of this. How does this work? Well, we're going to run their notebook. The great thing with Unsloth is, and by the way, if you're not familiar with like LLMs at all, and what does Llama 3.1, 3.2 mean? a lot of AI labs are releasing LLMs that they develop for the community to use and develop on. So these already come out of the box with a lot of great conversational skills. Like the Llama series of models are generally considered like the top tier performance. These come from Facebook, Meta. They have different sizes. Yeah, top tier performance on various benchmarks like coding, natural language reasoning. And you can have them in different sizes. 1B means it's a 1 billion parameter model. This will typically require a few gigabytes of memory just to load on your machine. You can have larger ones like 3B. And you can have even larger models if you wanted to, like 70 billion parameter. There's a 405 billion parameter model for Llama. That one's their frontier model. It actually has a very similar performance to GPT-4. Models like GPT-4, by the way, although I don't know if it's fully known, are probably 1 trillion parameters. So enormous models when you think of the parameter count on them. The great thing is with these libraries is we can actually play with these models ourselves. We don't just have to go to some website and talk to it and go through all those layers of abstraction. I can actually hold the model in memory and do things with it. So what is this? This is some esoteric representation of a model. But I want you guys to become, one thing I want everyone to be familiar with is this LLM is just some data structure that has a bunch of different modules in it that I'm going to explain to you. But first, I'll just show and then pique the curiosity, show something interesting, and then we'll go into the theoreticals. It's really just layers and layers and blocks of fine-tuned matrices with fine-tuned values in them. If I actually wanted to, I can go and figure out what is in this one particular layer. So if let's say I want to grab the state dictionary. Now this is going to be this is the LLM, by the way. What I'm scrolling through, this is the entire LLM that billions of dollars goes into developing and tons of compute. Now this is going to take me a while to scroll through. But all it's really showing is the different layers composed in it. And these are sequential layers, sequential transformer blocks. For the model at layer 10, there's a block called self-attention. There's this thing called the value projection, V projection, and it has weights associated with it. These are the weights, or at least some of the weights. When we're fine-tuning them, and when we're developing these models, we're actually just doing nifty tricks to modify these values, which we then are able to actually, through the tuning of this model, get better performance some way, somehow. Seems a bit mystical, but hopefully I can demystify that maybe a little bit this session and then a lot in the full session. But anyway, that's that's our model right here in all its glorious weights. Another very important concept when tuning LLMs, and this is what people do in industry, if you do get to actually work with developing LLMs, and I can teach to you as well, is parameter efficient models. So for context, a model with 8 billion parameters is going to take up many gigabytes of memory to hold. And then quick high level math, when you're training a model, you actually need to store multiple copies of it. So then you've gone from a few gigabytes to multiples of a few gigabytes. And you need to store what's called the derivatives when you're doing backpropagation. So even though it's an 8 billion parameter model, and let's say just for simplicity that takes 8 gigabytes of memory, you'll actually need multiples of that to train this model, maybe 32 gigabytes of memory, which then, okay, I mean, for most GPUs, that's starting to push. And for most people, that's more memory than they can hold. The nice thing is when we train LLMs, like I said, there's one model I have in memory now is actually a small one, just for the sake of making sure we don't have any issues. 1 billion parameter model, kind of small, but Llama released this just like a month or two ago, and it's pretty good performance for a 1 billion parameter model. Maybe one thing I can do if possible down here, is just show you by chatting with it. So I should be able to have the model here. Great. I'll actually text stream here. I can use these utilities. And it should, what I'm asking it, just for context, is continue the Fibonacci sequence. And oh, here you go. This is in real time, me actually communicating and chatting with this model. Okay, here's the continued Fibonacci sequence. I showed it, blah, blah, blah. And then it continued from 8 to give me 13, 21, 34, 55, 89, blah, blah, blah. And then kind of walk me in. So here it goes again. This is what Meta has handed to us. And I could ask different questions too. Now, maybe this might error, but I'm curious, who is the president of the USA? Oh, we can fact check its knowledge. Cool. And it actually says, I'm an AI. I'll be providing accurate information up until my knowledge cutoff of March 1st, 2023. As of the cutoff, Joe Biden was the president. Correct. Cool. Great. So just from this notebook alone, you actually have the powerful of a pretty strong LLM in your pocket. And maybe if you guys are familiar with programming, I could say, hey, write me a program to do binary search on a list of numbers. That's a pretty decent coding tool as well. If you notice that actually, so here, the benefit with this and versus using something like a chat GPT is I have full control over the model generation parameters. This is kind of abstracted away from you, but you can control the actual generation strategy, which in itself is like a 1 hour session of LLMs. But I said, I just want you to give me 128 new tokens. That seemed to be too low. For some reason, it's giving me C++ now. Fine, I didn't specify it. But here it goes, and then eventually it'll hit an end of sequence. Or maybe it'll keep going. And you see, so now it stopped because it hit 256. But not to get too much into this, boom, notebook for loading these LLMs, and you can load the more powerful ones if you want to. For fine-tuning the models, quick idea here, and again, Laura, the one parameter efficient way to tune a model, just for context, instead of training, let's say, all 1 billion parameters, there's great new research techniques to say, I just want to train a fraction of these parameters. And what the research has shown through techniques like LoRa, which stands for low rank adapters, low rank adaptation, you can greatly reduce the number of parameters you need to train, which A, helps you from overfitting. So your model doesn't fit too much to your data and still maintains its generalizable skills. And B, greatly reduces the compute and memory requirements that are typically very high of training LLMs. So as it says here, you can add LoRa adapters, so you only need to train 1 to 10% of the parameters. And we can very trivially just apply that to our model through these great libraries, right? Again, LLMs are composed of modules, so all I'm saying here is grab these modules. I'm going to do some math that we don't have time to get into, but now I'm going to train far less parameters. And not to spend too much more time on this, but I'll kick it off. It's good to see, like, explicitly what do LLMs expect as input? Here, we're actually going to train an open source data set that we're able to grab from Hugging Face. I'm loading it in memory, and I can actually go and grab this data set right here. I can see what's in it, conversations, source, and score. There's 10,000 rows. Maybe I want to grab the first one. This will load. And we actually see what is a conversation represented in a data structure that is expected. All it is, if you are ever wondered how these LLMs know how to become conversational, it's not magic. What we do and what AI developers do is we give it text in the format of some delimiter. Human said this. Human said this. And then we just append to that. Okay, AI assistant, maybe GPT, says this. And if you want to have a multi-turn conversation, you just pass that turn of conversations in as raw text. Human question one, AI assistant answer one. Human question two, AI assistant answer two. And then the latest question is just appending to this whole thing, human assistant or human question three. Now here, there's some standardization going on, but we can look at, again, one example. How do LLMs know this? Again, it's a lot less magical than you think. Just to show how interesting this is, I always found this interesting because it demystifies it. This is one full data set example that you would give to an LLM to teach it language and how to operate as an assistant. You use these esoteric tokens, which are actually called, you can call these special tokens for, let's say, chat templates, to explicitly tell the LLM, like, sign it as if it's has no idea what's going on. This is a system message. And what it tells the LLM is, before anything else, you have a knowledge cutoff as of December 2023, and today's date is something. This actually comes from the AI developers. Then explicitly, okay, here is the user saying something. And then the answer question. Start header ID and header ID. User. User asks some question. And then you explicitly tell it, hey, that is the end of the user's turn. EOT ID, end of turn ID. And now it's the assistant's turn. Okay, so we have the assistant header ID. And then this is what the assistant should answer to the user. This is the behavior we're demonstrating. And that's crazy, but this is it. This is the string of text we actually give to the model and train it with. And now I don't want to spend too much more time since we're already half an hour in. Again, the compression of all of this content into an hour is tough, but we can use these tools from TRL. This is Hugging Face, Transformers Reinforcement Library. Use these nifty tools to actually create a trainer object. We don't need to get into the details, but I'm going to specify my training run. I'm going to let this run while I jump into the next part of the workshop. But I do just want to, we have a lot of data. Let me stop this. I really don't need 100,000. I think 10,000 is fine. I believe I grabbed this up here. Split train, and I believe I can just grab the first, let's just grab the first 1,000. Data set. I don't think that one's going to work. Well, it's fine. We don't need to solve it on the fly. I will let this go on. But just to give some context, I'll create a trainer object from this nice nifty library. I will have to, well, here we go. Run, remove that. Map it, look at the conversation. Bear with me. Great. Okay. So while this does some mapping, I'm going to do some other setups that we don't need to get into now. And then actually, this line right here is the LLM training. Okay. We're going to be able to see the training loss, which is the performance. You can think of the errors, loss equals errors of the model. And ideally, as we train this, we should see loss go down. So I'll queue this up and we'll come back to it in a bit. I do want to take a pin/pause here. We're about halfway through. Oh, can you share the notebook? Sure. This one is super straightforward. Again, I'm sharing screen here. This comes from Unsloth. library, which Unsloth mostly leverages like Hugging Face and PyTorch. So it's just light wrappers on those. We can go to their notebooks, which for some reason not letting me click. Oh, it's because I already have the notebooks. Cool. This one is Llama 3.2. So I can actually just grab this and I'll drop it in the chat for all those who are curious. And again, Unsloth themselves provide you with free GPU to test out their code, their library. Great for this experimentation we're doing. Okay. I think I showed you guys something you can take home now and try out and experiment with and have a lot of fun. Now, I want to kind of break down and give you an idea of how we think about these fundamental building blocks. I don't know if I'll be able to do all of this in the next 25 minutes, but I'll try my best. A lot of the things you saw can be broken down into a few different categories, right? I think the first is how do we represent words as numbers? And maybe to go even before that, why do we need to do that? Well, I think like I showed you in this notebook, and these are still cute, everything's going well, great, data prep. The LLMs are a series of numbers. Computers understand numbers. They don't understand words and images inherently. We need to translate them to something they do understand, which is just this, floats, numbers. We take those numbers, we do some math on them, we do multiplication and addition, and we get numbers out. Cool. Well, the first part of that is how do we represent words as numbers? We don't do that as humans. Well, this kind of breaks into another concept first, which I would actually describe as tokenization. This is the process of, you think a sentence, we have letters and symbols in, let's say, the English language, 26 letters, 10 digits, and a whole bunch of symbols like $, up arrow, asterisk, whatnot. So let's just call it maybe 100 unique symbols that we recognize in English, in the human language. We need to do something similar for LLMs, but typically not at the character level for various reasons, because it would be very slow. Again, what is the goal of LLM? Predict the next token at a time. If we're predicting the next character at a time, while it could work, would be very, very slow and expensive. At the same time, going word by word is, well, it's beneficial, but typically we want to kind of create a vocabulary of the LLM language that we will now call tokens. Tokens are words for language models. There's some context here. It's a crucial first step because models can't interpret text directly. They need numerical representations. Tokenization converts raw text into a sequence of token IDs, which corresponds to a vocabulary, right? So here's just one example, just to go into the details. I'm loading a model called BERT-base uncased, and I'm actually going to tokenize this sequence. Transformers are wonderful, groundbreaking models. Okay. Now we've mapped, just to go through this notebook, transformers are wonderful, wonderful, groundbreaking models. And let me just make sure this will all go through. Yep. We've mapped this to the following token IDs, right? And I do want to run through all of this with you. So let me just make sure this can run. If not, we should be fine. Great. We've loaded it, no issues. And we can run this. Colab is a bit slow sometimes, but so be it. And what you'll notice is actually the loading of the model is quite heavy. This is the line that we're getting stuck on because these are still like many, many million parameter models. Yeah, actually, million parameters. But just to continue on, we had that sentence, and what it did is it converted the string to a sequence of IDs, and actually those IDs map to individual words. So token ID 19081 maps to transformers. 6919 maps to wonderful. Right? We can run this. And it adds some I guess, prefix to basically say, hey, this is the start of a sequence. And then something at the end to say this is the end. Share the workshop notebook. Good question. Unfortunately, I don't know if I'll be able to do that at the moment. I don't know if this is shareable, but I can share it at the end just to give context. And then what you'll notice is it's actually mapped groundbreaking to 3 different tokens: ground, dash, breaking. Okay, cool. And what you also might have seen is a very useful data structure in and honestly, all of deep learning, neural networks, LLMs is a tensor. Again, no need to get too much detail into it. All the detail is here. I won't run through every single sentence, but a tensor is just a very useful way to store and represent multi-dimensional numbers, especially. But it has some added capability to run computations on GPUs. That's why if you follow, the market at all, GPU companies are very, very important right now. Because the thing with LLMs is it's just number computation. Instead of, you can imagine you have 1 billion numbers, or you have to do 1 billion operations. Doing them sequentially is very, very slow. You would wait forever for your ChatGPT to answer if it did that. Instead, you can really parallelize that computation because a lot of them are independent of each other. So instead of doing 1 billion at once, you can do 1,000 computations of 1,000,000 in parallel. That's a lot faster. And GPUs are all about parallel computation. So anyway, we have the ability to use these frameworks, not to get into it in the actual lectures. We would go into more detail. But we can understand, hey, do I have GPUs? If I do, how many do I have available? Right now, I don't. In the Unsloth library, I would. This would show available. Cool. Okay, let's move on to the next part, which is we've found a way to map words in the English language, a sequence, into concrete vocabulary for LLMs that tokens. That's step 1. But tokens, as we saw, are still words. Like they still map to a word. So, okay. And you can say, oh, maybe I can use that number. And you actually could use this number. But now we're going to go into maybe a next step that honestly, this part alone, embeddings, is something you could design a whole course around. But I just want to give a high-level summary. Embeddings is like ultra fundamental to transformer models, to language modeling in general, and so much of actually machine learning. So what embeddings are is a way to convert words or tokens into not just one number, but a vector of numbers, a set of numbers, right? We'll use the word vector. And that somehow captures the semantic meaning of the word. So somehow we're able to take the word ground, okay, that's a token, and then now create a array of numbers that represents that word some way, somehow. Just to give context, the most important concept for embeddings is that embedding vectors are learned during model training, and actually they can be learned on their own, such that the whole goal of what you want is similar words should be similar to each other in the vector space, right? So a good embedding space, words like cat and dog should be closer to each other Embeddings, you can just think of a simple three-dimensional one as a point in a three-dimensional space. And the word dog is somewhere in that three-dimensional space. It has 3 dimensions, 3 numbers, a vector of dimension 3 associated with it. Cat is somewhere else. And because they're both animals and share a lot of common attributes, they should be close to each other. Versus the word cat and car should be very far or relatively far from each other because they share much less things in common. So this is some magic, really, but it's honestly just machine learning and math to semantically represent similar concepts as numbers. So in transformers, they serve as the first layer, converting words into numbers, and we can actually play with this. So let's extract from our model that we loaded in what the embeddings are. I had that sequence, by the way, if you remember. Inputs, this is my actual IDs. This actually just maps to, if I recall, yeah, this is just the token representation of my text. Okay. So I map text to inputs, and then I give it to my model, and then I get some outputs. And then what I can do is actually see, okay, I have this thing called embeddings now. Let's take a look at what this is. Embeddings is a multi-dimensional array. Okay. It has, if I grab by the way, the shape of the last, maybe let's do this. I just want to walk through it with everybody. This is again the token representation of my inputs. It's 1 row, 11 columns. That's how you can think about it, right? What's the shape? 1 row, 11 columns. Cool. Well, now my embedding shape is 1 row, 11 columns. And then also each of those 11 elements has something behind it that is of dimension 768. So let's look at it. Let's walk through an example here. Okay, we're going to look at the word transformers from our input, right? It has a token ID of 19081, which I'm printing out. And it has this maps to an embedding of shape, 1 row, 768 columns. We've somehow taken this word and represented it with actually a series of 768 numbers. And here are these numbers. This is the embedding for the word transformers. This is how we represent it. And again, the whole goal, not to get into the details, but we actually train a model to develop what these numbers should be, to teach what these numbers should be, with the whole optimization of the model to make sure that similar words should be similar to each other in this space. Now, we're humans, we don't understand the 768 dimensional space, but we understand 2-dimensional space and 3-dimensional space. It's the same thing. Imagine a 2 or 3-dimensional space, but more dimensions actually allows you to capture more signal, more intricate details about a concept. So we can skip that, but here you go. This is the word transformers represented. And we can actually visualize it in 2-dimensional space. Now, again, kind of simplifying things a bit. We can use PCA, which is just a way to project a high-dimensional space to a low-dimensional space. Let's take the 768-dimensional space and project it onto a 2D plane. It maps to this. Now, it's hard to pull too much meaning from it because it's just 2 dimensions. But you have a component A and a component B, and you see where these words map to. So, for example, in this context, groundbreaking are very close to each other. Models is closer to transformers than any of the other words. And you can start pulling out some other like semantic representations. And then this separator, which is a reserved special token we don't need to get to, is intentionally supposed to be different from all the words. This is basically a token to tell the model to stop talking. That's one way to think about it. Like, hey, when you see step, stop. So it allows it to think about how far it is. It's a very different behavior that comes with this token. Now we can play around with this for a lot. I know this is kind of like drinking from a fire hose, but I do think it's very interesting. So that's kind of embeddings, and that's how we'd map words to numbers, and then we can actually feed these numbers directly into the LLM. And then the LLM will output numbers back. And based on those numbers, we can actually take those numbers, map them back to tokens, and then, hey, this token had the greatest likelihood. That's what the LLM predicts. So the next word in the sequence is blah, blah, blah. Speaking of training, let's see how we're doing here. So we have, again, max memory just showing of 14 gigabytes. 2 gigabytes was used, and our training operation completed. It took 3 minutes. Keep in mind, it took 3 minutes because we did very few steps. Just to go back into the trainer. Go bananas with looking at the documentation here. But essentially, I just told it to say, I want you to take 60 steps through the data set that we have. Or actually, sorry, not 60 steps through the data set. We're going to split our data set into batches of 2. We'll do some other stuff. Basically, this is a very small fraction of all the data we have available, so it finished relatively fast. But hey, look at this. From step 1, now our loss function is a bit messy. We should see that our training loss is actually coming down. Again, it's noisy, but I've trained over 60 steps. Surprisingly, it doesn't. And the answer here is because you really need thousands of steps to start seeing like the prototypical loss curve of a LLM go down. But this is the error going down over time, but so be it. Keep in mind, and just to show you some summary stats from this training, again, I want to give you a takeaway. I know we've moved very fast. A 1 billion parameter model took up 2 gigabytes of RAM, right, of reserved memory. But to train it required a peak of 3 times that, right? Because of this duplication of states that we need to persist when training the LLM. Great. And this is a very small model. GPT-4 is 1,000 times bigger than this. That's a lot of compute that you need. But now this model should be a little bit more adapted to whatever data set I gave it. So I gave it a data set, which I kind of just glossed over, of seemingly like random facts about the world. If I wanted to fine tune my model, let's say on specifically being good at programming, I would give it a data set that is dedicated to programming. And I would see if the training went well, that the model actually now performs better than before on programming tasks. We can go through operations, we can save this model, but come back to this part. Maybe I can say, hey, just tell me about astronomy. We can change the parameters, saying I want it to generate up to 512 tokens. And by the way, just so it connects, as you see, like the words come out 1 token at a time, because that's what the model is doing. It takes all the words that came before it and is using it to generate the next token. So that's what allows us to actually stream LLM responses. Otherwise, you'd have to wait until all of this is complete, which we don't need to do. There's other fun generation parameters you can change. For example, temperature. This kind of controls the randomness of the LLM. If I make this, let's just say I duplicate this somewhere else. If I make this very, very small, it may change the response. We'll have to see. Yeah, actually, you can see now it's going down a different path. There are several subfields of astronomy. That's not what it said here. Now, the concepts are similar, but it's not the exact same text. So now there are all these fun things we can play around with when doing generation to get different responses, different diversity of responses, and so on. Cool. And I see one question in the chat. Again, unfortunately, I think I put too much content into the workshop. So and we need it's a lot of interesting, really cool concepts here, but they take time to really understand. Somebody asked what particular aspect of the data does a model depend on to create embeddings of a token? Okay. Let me try and give this as a fire hose explanation because it's critical to how transformers work and how LLMs work, but I might need more detail. The embeddings I showed you are standalone independent, right? So you can imagine an embedding for a given word represents some point in space, in some n-dimensional space. But we know that, and these embeddings are somehow representing like the semantic meaning of a word. But the meaning of the word changes depending on the words that are around it. For example, transformer on its own can mean a lot of things. Transformer can mean like the action figures or the TV show. Transformer can mean a concept in electrical engineering. I think does, I'm not an electrical engineer, so I might get this wrong. Like some conversion of energy and electricity. Or transformer can mean this LLM architecture. How do we know? What a good embedding system actually does, and this is where the attention mechanism comes into play, and why, if you've heard of the paper, attention is all you need, self-attention. That is the whole goal of attention. How do we take a standalone word represented as an embedding and imbue it with the context of the other words around it to add that context to the word? So now it's not just transformer with no context, it's transformer in the context of a model. And then that changes that. Actually what we do is we actually move that word in the embedding space somewhere else that somehow moves it closer to having the meaning of transformers based on machine learning models. Cool. And now we have a new space, a new embedding that has been moved from the original one that captures this information semantically. Again, that is where we come into self-attention, right? Let me just walk through this. It allows transformers to relate different words in a sentence to one another, regardless of their distance. There's also other things that get into this, but whatever, self-attention. We have these concepts of query, key, and value, which we honestly don't have to get into right now. But basically, these allow us to figure out how to relate different words to one another. Then all we do, and I walk through an example here. I'm just going to run through it. These are some toy examples. You guys are free to play with this. We can kind of compute attention. And here's the biggest thing I want to show. Visualizing it. Okay. Cool. Hopefully this is something that gives some context here. So for a given word, how much attention should it pay to all the other words? So how much should transformers pay attention to, let's say if I'm looking this way, pay attention to all the other words like wonderful. Maybe a better example here is models. How much attention should the word models, or yeah, how much should it pay attention to the word transformers? Okay, some amount. How much should it pay attention to the word R? Wonderful, groundbreaking, so on and so on. And this is kind of telling you, and again, this is a naive, contrived example. So in sophisticated systems, it would be a little bit different. But you would see that something like the word breaking is paying a lot more attention to ground. So again, breaking can mean many things on its own, but we've actually taught it to pay attention to ground because groundbreaking means its own thing, and to pay attention to the dash because this is now imbuing the word breaking as a standalone embedding with the context of groundbreaking. So now it's actually the next step of this is we actually change the embedding of the word breaking to factor these components in. Hopefully that makes sense. Again, complicated, needs a bit of time here. In this example, I actually do show how this will happen. So for example, we actually can compute these things. We can compute the attention weights I just showed you. And if you see, like, again, we have the embedding shapes, we have the attention scores. The attention scores are the same thing. For each word in the sequence, how much attention do I pay to all the other words in the sequence? So it's of shape 11 by 11. I can look at one of them and it tells me, hey, how much weight, attention, should word 5, right? It says 5, we count from 0, place on each of the other words 0 to 11 in the sequence. This tells me it. Great. And then what I actually do is modify, I actually create a new 768 dimensional attention output, right? And I add this to the embedding of the, let's say, the fourth word. It gets a little bit complicated here, but okay, we've added an embedding to some other embedding. Cool. That affects the meaning of the word, and that actually helps the model understand what we're talking about. There's another concept here, so it's not just the words, but the position. So you can also say, hey, I mean, how much attention should I pay to the first word and second word? And you actually can imbue embeddings with the information of what position in the sequence that they come in. We won't have to get into that, but can be done. There is an end-to-end example here, and I just want to walk through this very quickly, and then I'll kind of summarize. Let's say I have the sequence, hello, how are? I tokenize it. I get these tokens. I calculate the embeddings. Okay, there's 5 tokens. Each of them has an embedding 768. Let's calculate the self-attention mechanism. Okay. So I've basically determined how much each word should pay attention to the other words. I do some other, just stuff that helps stability, like layer normalization, whatever. Fine. And then I actually construct a neural network, a very trivial one, to take these inputs, right? And then create some output. Finally, what I have is, and I know we're going super fast, the ability to predict the next token. So that we use the output of the attention mechanism in the embeddings to get some output, and then we take that output and we're actually able to compress that into a prediction of, okay, what token should come next? If I take my predictions, by the way, which come out here, I'm actually able to say, and I'll just skip through it, I'm able to predict the most likely next word based on what the model has learned is most likely, and go on from there. Now, keep in mind, I used a randomly initiated neural network to do this. So it hasn't been trained. So what's this model going to do? It's going to output gibberish, which is what we're seeing. But if I trained it, if I actually modified the weights to against a certain task, I would see that, hey, probably the word that comes after hello, how are is you. And maybe the thing that comes after that is a question mark. And then after that, then that's a point where it's actually very ambiguous what should come next. But depending on the model training, it'll continue the sequence. So again, hopefully this kind of demystifies what is happening under the hood. It's a lot of numbers, but as you start to build the intuition, it's just a series of, very smart people have figured out ways to represent words with semantic meaning through numbers. Again, through transformers, we figured out even better ways to keep meaning throughout a sequence. and then finally use this sequence to predict what should come next. And somehow we get these phenomenal tools like ChatGPT and Claude that, through having seen literally trillions and trillions of sequences or words, are able to very much predict accurately, most of the time, what should come next, which is kind of magical. But this is the foundation to it. And just to give one, by the way, why these tools are not perfect. I don't know if you guys have seen this example, but this is one that always trips up LLMs. How many R's, I can't type right now, are in the word strawberry? Okay. Here's the thing, because they're doing next token prediction, LLMs don't actually, like we do, go and individually count. They don't have a concept of counting letters in a word. All they're going to try and do is predict what should come next, but they're not counting at all. But typically, there you go, it gets this wrong because it's just predicting from how many R's are in the word strawberry, it predicts there. From how many R's are in the word strawberry there, it predicts R. From how many words are in, or how many R's are in the word strawberry there are, it predicts 2. And it just got it wrong. But now, because it's predicted 2, it's just going to continue on. Or the concept of current time, and same with raspberry. So, there's a lot of magic and amazing utility in this transformer architecture and next token prediction, but it's not exhaustive. And here are some, limitations of this. Now, one thing I can do is, because LLMs just predict the next token, if you kind of force it to think first before it has to commit to an answer, it typically forces the LLM to go down a generation path that makes it more correct. This is called like chain of thought reasoning, but please explain your chain of thought first before answering. Typically, this gives better responses. Well, unfortunately, it just, it looked really good, but unfortunately, it's not foolproof, right? Like, again, they're not counting. They don't have this idea of actually deterministic state. Everything they do is probabilistic next token prediction. How many threads of interest are needed to predict? This is hilarious. So unfortunately, it still gets it wrong. Typically, this is a very small model. Maybe a bigger model would get this right, but hey, it tried. Yeah, so hopefully that keeps you in mind. By the way, because of this, LLMs don't really have intuitively a sense of uncertainty. Once it's predicted 2, it's just going to go with the flow. It's going to say, oh, like it was 2 in the sequence before, I'm just going to continue. And you can actually, you can basically gaslight it to do things that are obviously incorrect. Like explain why there are two R's in the word strawberry. I can make this more ridiculous. And typically in fine tuning, you actually try and align the model to not fall for these like traps. But right, so it's just saying random things. Or because it is type of fruit that is typically red in color. And it sounds very confident, but this is completely wrong. And the thing is, we know this is wrong, but when it gives you code sometimes, or when it gives you factual information and it says it so confidently, it seems right. But be careful, because the architecture of transformers doesn't have this idea of uncertainty built into it. So it's just going to go along with the flow. Whatever the sequence has been so far, it's just going to keep appending the next likely token on top of it. But at the end of the day, sometimes next token prediction is great because for coding, a lot of the times it's just generate the next token. There's a stable idea of what should come next, and we get some great code. So hopefully that kind of gave I think that's all I wanted to cover today. hopefully that kind of gave you guys something to take away with. You can literally take these notebooks and run them yourselves, train your own LLM if you want, go into the nitty-gritty. And then hopefully you have a little bit of a better idea of the actual fundamentals going on behind the hood. Again, these are concepts that take, you will not get them on the first pass, but with multiple passes, hopefully become more intuitive. Hopefully this notebook helps visualize and illustrate that so it's more intuitive. And hopefully everybody on the call learned something new. That's my goal. And hopefully it was interesting. So that's all I wanted to share. I'm seeing requests for the copy of the Colab notebook. Um, let me do this. What is the easiest way I can share this? Save a copy. Da, 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 da. Because the thing is, if I share it, I don't know if we all go on the same notebook. Before jumping the gun, I'll talk to Murat and the team and make sure, we can share this in a reproducible way. We will. Hopefully it helps you learn. So yeah, that's it for me. Thank you all for sticking around and listening. I think a lot of people stuck around, so that gives me some hope it wasn't too much of a fire hose and was somewhat interesting. Cool. Thank you.